the whole idea of statistics. We collect information, that's the first part. Then once we've got the information, we present it, whether it be in graphs and tables, whatever. Then we analyse it. And then I guess the last part then is this, statistical inference. So what's the point of collecting all this information? It's so we can go and infer something and make a decision. So let's look at this idea of statistical inference, where we use the data to infer different properties about our probability distribution. Now, things we have to assume. So it assumes that our sample data set, we've got a sample, we can use that to make predictions about the whole population. I mean, it's very hard to gather 100% of data for some things. And so we just look at a sample, and from that sample we say, well, okay, we'll infer that about the complete population. So what is sampling? Well, that's exactly what I was just talking about, where we just select some elements from a population. It might be a finite population, it could be an infinite population. But why do it? Well, it's going to be quicker. It's going to be quicker than trying to gather every piece of information. Cheaper. I mean, if you're paying someone to go out and survey people, it can be a lot cheaper to survey for a sample than can you go and talk to every single person. Accuracy, this is the interesting one. It's actually more accurate for a sample than it is for the whole population. Because once you start talking about really big numbers, well, we're human, we make mistakes. So it actually is more accurate. And necessity, and there's the example I've got there, matches. You can't possibly test for quality of an item if by testing it you're going to destroy the item. Imagine it. Got this box of matches. I'm just wondering how many of these matches are defective. That one worked. That one worked. I mean, it's ridiculous. Obviously, you're not going to go through the whole box of matches. How should you do it then? What's a good way of doing it? This comes down to random again. We had a bit of a chat about what is random the other day. But we always try and do it randomly. But a sample will be random when each element in the population has an equal chance of being selected. And so there's no bias at all. It doesn't necessarily mean you're going to get a cross-section of the population. Right, so you might think, well, in this class, at the moment, if you look at, say, ratio of males to females, and so we go, well, we want a sample. It doesn't necessarily mean that sample would have the same ratio. Okay? It doesn't have to happen. So some terminology. If we're talking about a population, then when we collect the data, we call that a census. And I suppose the most common one that you would hear of would be that one the Australian Bureau of Statistics does every, 4 years or so. Sample, we call it a survey. So if you're only getting a sample, that's then a survey. Notation is slightly different too. When we're working with a population, we call it the probability. Whereas if it's just a sample, we actually call it the relative frequency rather than the probability. And so the symbol there you'll see is F. Expected value, the symbol we use for average or expected value, in a population we use the Greek letter mu. But if it's just a sample, we use X with a bar over the top. Variance, sigma squared for population, but S squared when we're talking about a sample. Now what should happen? As n, so the size of your sample increases, then your sample expected value and variance should approach the population sample and variance. And of course, once you've got the whole population, it's going to be exactly the same. So 2 dice a roll. Theoretical probability distribution would be on the population. Because theoretically, if we were to roll our dice an infinite amount of times, we would get the population results. So the actual probability and so on. So I've drawn up a little table here. There's all the possible outcomes going from 2 to 12. The probability of them happening I've worked out there. So I've got them in for us, and yes, they add up to 1, which we're expecting. And speaking of expecting, xpx did that column, and x squared px have done that column as well, even though it's a row. Why I just called it a column, I don't know. So the expected value, the sum of xpx, is 7. So when you roll 2 dice, most logical answer would be I'm going to get a 7. The variance is 5.83 repeater. That means the deviation, find the square root of that, and that's probably an approximation, I would imagine, 2.4152. If I was to graph it, it would look like this. So theoretically, you've got a lovely symmetric graph. So now we're going to, well, we're going to pretend, we're going to do a simulation, but roll a pair of dice 50, 100, 500, and 1,000 times and compare these samples with the population. And yes, I did this 50, 100, 500, and 1,000 times, but I'm not silly. I let a spreadsheet do it. I wrote the program for the spreadsheet, so it rolled dice that many times. Now, when I did it 50 times, so the first 3 rows, there's our theoretical probabilities. Underneath, you'll see I've changed it to relative frequency. This is what happened when I did it 50 times. So you can sort of see it didn't necessarily fall into the same pattern. The expected value was 6.42 when I did it 50 times. So the difference between the theoretical and the relative one when I did the experiment there, it was out by 0.58. The variance turned out to be 5.8036. So the difference in the standard deviations was pretty close, 0.0061. Now if I was to graph them both, so the diamonds were the theoretical one, the asterisks there are the relative frequency, doesn't really match. It's got a bit of that up and down pattern, but doesn't really match it that great with 50. Okay, this is what happened when I did it 100 times. So now it came back with an expected value of 7.16, difference of 0.16 on the average there, and variance 5.9544, gave me a difference in the standard deviations of 0.025. There are the graphs of the two. Let's get a little bit closer. 500 times, there's what happened. Average 6.86, difference of 0.14. Variance 5.644, difference in deviations 0.0394. Getting a bit closer now. And this is what we would like to see. More times you do it, these graphs would hopefully fit on top of each other. 1,000 times. Ooh, 7.042, so very close there. Deviation out by 0.0619. Not too bad. I could have kept going and increased the number, and as I say, hopefully we'd see it. Now, I promise you that was purely random. I haven't just made those numbers up to make the example work nicely. It is honestly what happened when I went and did this. And that's why I'm always pleased when it turns out well, because I go, phew, thank goodness it's going to prove what I want to say. I mean, it is of course theoretically possible that it could have looked completely different. But that's the thing, when you do it 1,000 times, sure, you might get some that's way out, but then you get enough that are close to bring that way out and back into line. Not a lot of questions on this one. 13Ds, well, it's a little bit different sort of exercise, statistical inference. Have a look at these 4 anyway.